Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 4 Chemistry students. Welcome back. Alan is my name, still interacting with you in chemistry lessons. I hope you're fine. So we are concluding up our Unit 15, which is about factors affecting chemical equilibrium, and that is the subtopic of chemical equilibrium. So, as usual, I always highlight what we are to look at and the key terms and objectives. So, this lesson, it is lesson 4, and we are going to look at industrial application of the factors affecting chemical equilibrium with much emphasis on the factors that affect ammonia production, and that is change in temperature and change in pressure. So we are going to be looking at how changing in temperature and pressure affect the yield of ammonia in the Haber process. That is ammonia production in industries. So again, our key terms remain equilibrium composition or mixture, equilibrium position, and the shifting to left or right. Left if the reactants outweigh the products. Left for reactants and left and right for products. So our key objectives are: 1, to interpret correctly the different graphs and identify the possible conditions, what we call theoretical conditions for production of ammonia. In other words, we use the knowledge we've already covered to predict what would happen if you increase temperature or pressure in relation to ammonia production in industries. So then after we've predicted and identify the possible theoretical conditions, then we can go on and relate those theoretical conditions and the actual conditions that are applicable when they are producing ammonia on a large scale. So those are the two objectives we shall look at. So much more of today's lesson will be on industrial versus classroom or versus room discussion. What happens when you discuss and what happens when you go directly into the industries and find out the conditions. So a quick recap of what we looked at, the factors that we shall be looking at. We looked at the effect of changing temperature, whereby whenever you're having an equation or whenever you're having a reaction, then you must take note of the temperature. How will it affect? By looking at the enthalpy change for that reaction. In this case, this is exothermic and backward is endothermic. So when you increase temperature, you will favor the backward, which is in the direction of endothermic section. In other words, increased temperature favor endothermic reaction. Changes in pressure. Increased pressure, you will favor the reaction which involves fewer gas molecules, because when you increase pressure, you reduce the volume. So the equilibrium shifts to counteract the decrease in volume, and that involves decrease in the number of moles, applying Boyle's law and Avogadro's law. Then the other factors we looked at is the concentration. Of course, this depends on whether you're reducing or increasing the amounts at equilibrium. Then the addition of inert gas, as we said, the inert gas does not take part in the reaction, but what it does, it changes the volume of the equilibrium mixture. And as such, it shifts the equilibrium to a side with higher number of moles or higher volume. Remember comparing Avogadro's together with Boyle's. Then we can get the principle that the number of moles occupied by, the volume occupied by a gas is directly proportional to the number of moles present, provided temperature and pressure remain constant. Then we ended on by looking at the catalyst, where we said, basically, the catalyst does not affect the position of equilibrium because it increases both sides equally. And at the same time, it does not affect the magnitude of the equilibrium mixture, but it only makes the equilibrium to be attained very, very fast. It simply increases the rate of attainment of equilibrium. It does not affect the position and even the amounts. So those are the factors we looked at, each in its own case. If you missed either of the lessons, I would implore you to refer into those lessons, lesson 1, 2, and 3, and make sure you catch up, you don't miss anything. All right, go with me on today's lesson, industrial application of equilibrium factors. And specifically, we're going to be looking at large-scale production of ammonia in the Haber process. When we say large-scale production of ammonia, yes, I'm pretty sure the word ammonia or the liquid ammonia at this stage of senior 4, you have gotten in interaction with the ammonia either as a gas in the chemical reactions or ammonia as solution for qualitative analysis. That is on a small scale. You use a few milliliters of ammonia. But normally, ammonia is produced on large scale for production of fertilizers, like ammonium phosphate, even to be used as an explosive. In World War I and II, ammonia was being used as an explosive in the war. Or it can be used in many other aspects. I've even mentioned of the lab activities, qualitative analysis, or quantitative analysis for acid-base reaction. So we use ammonia now and again. Even in some of the materials we use in cleaning, like the Windex for cleaning the windows, it has ammonia. So we use ammonia now and again, meaning it has to be produced in large amounts. And as we've been looking at, we notice that we are using a lot of nitrogen plus hydrogen giving ammonia. We've been using that equation. So now we are going to see what happens when it comes to industrial application of those factors of temperature and pressure. Let's get started. Right, this is our ammonia equation, and the raw materials are basically nitrogen, as you see, and hydrogen. We normally get nitrogen from air and hydrogen from natural gas. In Rwanda here, you know we have natural gas, basically methane in Lake Kivu. So if you wanted to produce hydrogen, you would opt for that methane gas, and Lake Kivu, you would get your hydrogen. We are surrounded by air. The air we breathe in, or what? In this environment, we have air. So in air, we have nitrogen. Mix nitrogen and hydrogen, then you'll get your ammonia. It requires a ratio of 1 to 3, 1 for nitrogen and 3 for hydrogen. Under different conditions, then you will get different amounts of ammonia. These conditions are basically within industries, and that is temperature between 400 to 450, pressure of 200 atmospheres, and the presence of a catalyst. You see, we are bringing in pressure, we are bringing in temperature, and a catalyst. So the main part of today's lesson is to see how are these factors, if you change them, how will they affect the yield of ammonia. Before I go, there is something I want you to notice. Unreacted gases are recycled. This point, we shall refer it to when we reach in industry. I want you to take notice of that. There is recycling, meaning they do not throw away what has not been used. Now, let's bring in our factors. I want us to take some time and interpret this graph. You have all the time you need. I'm giving you a minute. I want you to take a close look. Remember, mixing nitrogen and hydrogen to produce ammonia is ectothermic. It releases out heat. And the composition of nitrogen, of ammonia to nitrogen and hydrogen, or what we would call dissociation, is endothermic. It requires heat. So now, we are having percentage yield of ammonia related to increase in temperature as pressure is altered. You see the curves. Here we have pressures changing, increase in temperature, and increase in the percentage yield of ammonia. Pressure 10 atmospheres, 100 up to 1,000 atmospheres. So, with a minute, where do we have the highest yield of ammonia? What are the possible conditions where we have the highest yield of ammonia? In that case, I will just simply call them the experimentally expected or the theoretical, not in industries. So, in this case, where do we have the highest yield of ammonia? Take a close look at that graph, interpret it. Different conditions, but they all geared to the yield of ammonia. Let's do it together. Let's start with when you have temperature of 200 and at lower pressure, which is 10 atmospheres. What do you notice? Why is the yield? You notice it starts at 50%, but decreases as you maintain pressure and you increase temperature. The yield decreases. So let's move to 300 atmospheres pressure. Maintain it, but change temperature. You notice it is starting at around 90% yield at 200, but it reduces as temperature increases. And as you notice, we have highest yield at temperature of 200, almost 100, with high pressure. So if we can quickly write out our pressure and temperature conditions, high yield will occur at low temperature, which is about 200. This agrees with this reaction. It is ectothermic, meaning it occurs at lower temperature. Increased temperature, you favor backward. Point second. Pressure. We are starting with 4 moles. We are going to 2. Volume is decreasing, so indicating this forward reaction is favored by high pressure since you're compressing. So you notice even what is happening. At high pressure, about 1,000 atmospheres, we have the possible highest yield. So we'll call this theoretical. Because take note, what are the conditions for production of ammonia in industries? This is the industrial conditions. What are they? About 400 degrees Celsius temperature and about 200 atmospheres pressure. And what is the possible yield? If we extrapolate, it's about 40% yield. Now, I pose a question. Why are industrial conditions around 400 degrees Celsius and 200 atmospheres pressure and not these conditions where we have the highest yield? Why do they opt for these conditions with lower yield and not at conditions that can give us the highest yield? Yes, Now, this is the balance I want us to go through. I want you to understand clearly. This is the balance we are looking at. Theoretically, we've seen that the yield is this way. But in industries, these are the actual conditions. Why? Can we discuss that? I hope you have a thought. So, if you are already thinking something, you can share it or discuss it with a friend you're having. Then we continue. Let's now converge and find out what is expected. So, this is our theoretical conditions, or what we expect. But these conditions have some disadvantages, what we call drawbacks. So what are those drawbacks? First, you need to notice that at low temperature, where you expect high yield, the reaction is very, very slow, because the molecules do not have enough activation energy. What is activation energy? The minimum amount of energy required for to be possessed by molecules for them to convert from reactants to products. And this goes in with the kinetic energy. Let me use this analogy. Normally in cold conditions, when it is raining, for instance, outside, we tend to remain inside. We cover ourselves with jackets and remain inside doing some simple work inside the house. But if it isn't raining, then we would prefer to go outside and be active. Play soccer, visit friends, be active, be lively outside. You notice the point. But because it is cold outside, we tend to remain less active. The same applies to reactions. When the temperature for the reacting system is low, the molecules do not have that enough activation energy, enough kinetic energy for them to move and collide up with each other for them to form products. So at lower temperature, the reaction is very, very slow. You wouldn't yield a lot. Theoretically, we've seen it would work, but it wouldn't yield a lot because the molecules do not have enough activation energy. That's one. Let's look at pressure. Pressure comes with a few things. One, safety issues and economic implications. When we talk of safety issues, we're looking at a bigger picture. Suppose you've concentrated your nitrogen and hydrogen at a high pressure, and you've produced your ammonia in high amounts, and there is a leakage. Fuel in a system and the containers break. What happens when you expose that high amount of ammonia in the environment? What happens when you expose that amount of hydrogen, which is relatively explosive, in the environment? So you have to also think about the safety issues. Leave alone the safety issues. Even with high pressure, you require initial installment of equipment which can withstand that high pressure. And in that case, you require the chromium installations. So, and the chromium as a metal is expensive. So meaning, for you to carry out the production of ammonia, you would have to incur a lot of expenses in installment when you're installing the component, and in some time it may not come out. So from a business point of view, you find doing heavy installations would not be the best way. So you look at the leakages, which would be very detrimental, and the expensive part of installations. So what is the way forward? After you've seen low temperature, reaction is low. High pressure has its own disadvantages. So what do we do? What is the way forward? The solution is compromising. So the scientists had to sit and say, let's compromise. Yes, we know we can get over 97% or 100% yield of ammonia at low temperature of 200 and high pressure of 1000. But remember those other disadvantages. What about we run around and lower the pressure, but increase the temperature. So in industries, they opt for temperature of between 400 and 450 and the pressure of 200 atmospheres because of two reasons. One, with the a relatively higher temperature, the molecules have high activation energy, so the reaction is going to be relatively faster. With lower pressure, yes, so they do not have to incur installation of expensive materials. But remember, the yield is low, about 30% yield. But with this lower yield, do you know what happens next? You will get your 30% smaller yield, but it occurs at a faster, it occurs in short time, meaning you will be getting your 30% in short time, 30% in short time. If you add overall, then you get a relatively higher yield than waiting for the reaction to be slower for you to yield 100%. In other words, you're getting small yield, but in short time. So if you're using a whole day, you'll get more than what one would have waited to get 100%, but after like 2 days. That is a compromise. That is a compromise. And remember, due to lower pressure, we expect some nitrogen and hydrogen to remain unreacted. Because the pressure is low, they are not compressed high. So that's why the unreacted gas molecules are recycled. Remember, I started on by telling you that point, recycling. So as you compress with low pressure, gases remain unreacted, they are corrected and brought in back. So you continuously recycle your nitrogen and hydrogen, meaning you're not incurring extra costs in producing more of the hydrogen and nitrogen as raw materials. So you see, this is about the balance, which I want to tell you. Doing science does not mean you're outside of economics or you're outside of entrepreneurship skills. They have to work together. So do not just go into the books and say, me, I take chemistry, I only read chemistry alone. No, you also need that knowledge of business, that knowledge of entrepreneurship to balance up. So as when you come out as a scientist, you're not only looking at the chemistry molecules, but you also have the balance. So that is what we can look at when it comes to equilibrium, the chemical equilibrium and the factors that affect chemical equilibrium. They are actually applicable. Theoretically, you may think of that, but when it comes to industries, you have to involve a lot of it, but you do not leave out your theoretical knowledge. So on that point, I want us to quickly go through this exercise, which I left you in lesson 3. I want us to correct it as we conclude up this unit. So we had this question at 25 degrees Celsius and 10 atmospheres, the conversion of ammonia is 5%. We are to predict, explaining our reasoning, what would happen if the percentage, what would happen to the percentage conversion if pressure is increased while we maintain temperature constant, if temperature is increased while we maintain pressure constant, and you add a catalyst ion, what would happen? I believe you are tempted, but let's go through it for you to completely understand how to respond to these questions. Let's get started with part A. Let's get started with part A. This is asking predict, then explain, indicating it is a two-part question. You have to first state your prediction, then give the explanation. In marking, we always consider those cases. Do not miss a mark for predicting, and do not miss a mark for reasoning. So this is what is expected. When you're dealing with pressure, of course, you have to look at the equation. Left side, or the reactant, it is in higher volume than the product. So increase pressure, you will favor the forward. So the yield will be greater than 5. Why am I specifically saying 5? Because this is at the conditions we're having, and we are changing this condition. So your response has to be in terms of this equilibrium mixture which we are having. So it will be greater than 5. Reason is simple. Increase pressure, you reduce volume, so you disrupt the equilibrium. To counteract the decrease in volume, then more of ammonia, which is in lower moles, will be produced. That's first. Part B, what would happen if temperature is increased? Of course, as you notice this value, this sign has to direct you. So with this sign, it indicates the forward is exothermic, the backward is endothermic. And as such, increase temperature, you're favoring backward reaction. So the conversion will change, will be lower than 5%. Because the backward reaction is favored, and so you'll have more of nitrogen and hydrogen at equilibrium, since ammonia will dissociate because of high temperature. And lastly, if you add iron as a catalyst, remember a catalyst does not affect, one, the position of equilibrium, and the amounts at equilibrium. What it does, it only increases the attainment of equilibrium and the attainment of the equilibrium composition. So in this case, they will remain 5%. There will be no decrease or increase, but it will be attained in a shorter time. So you see how you can quickly go through these questions. Just take a few principles. Take just those principles, then the chemical equilibrium becomes enjoyable, isn't it? And as usual, I have to leave you with the exercise. This is equally like what we've just discussed. That is exercise 4, and that ends up the unit 15. You will find more of the chemical equilibrium in Form 6 when we're dealing at quantitative. This has been qualitative, looking at the factors, but you're going to look at quantitative in terms of the quantities. Exactly how does temperature affect the chemical equilibrium, but in terms of quantities, unlike this which has been in the descriptions. So that is the exercise. It is just simply about the industrial conditions. You see, the same question I asked you, now I brought it for your review, and this is just a trigger for you. And one large-scale use of ammonia. Please go through that. Include the signs in here, please, including the signs there. It's supposed to be reversible signs. Thank you for taking part in the lesson, and thank you for being part of this unit. I'm glad that I still interact with you. I hope to see you in the next unit. Please stay safe. Alan is my name. Bye.